Okay, so now we're going to go into the divergence theorem in section 16.9, but I want to go ahead and remind you of the notes in 16.5 where we had talked about divergence and I was trying to motivate what divergence means. Once we defined divergence in 16.5, we went back and looked at Green's theorem. And this is Green's theorem here, okay? And we were able to show that Green's theorem with a little working can be worked into a two-dimensional version of Stokes' theorem. But also with a little more working, I was able to derive something called the divergence theorem in 2 dimensions. And just kind of went through a big discussion. This is the divergence theorem. So let's just copy this. We're going to change it just a little bit to put it in 3 dimensions, but this is the gist of the divergence theorem. Actually, let's keep the whole interpretation here. Okay, so we're going to go up to 16.9 now. Okay, so again, this is section 16.9. It's the divergence theorem. Okay, and this will be a 3D version of it, but we'll paste in the 2-dimensional version like that. Okay, we're not going to do flux across a curve in a plane. We're going to do flux across a surface in space. The surface will be a closed surface. So basically, I just want to change the curve C to a let's say this a closed surface. Oops. S. Okay. And the integral here, I'm going to just nudge it a skosh and make this a double integral. And maybe move my clever little circle out of the way, because this one indicates an orientation that maybe would be confusing for a surface integral. But we are going to have a circle around this, okay? So the circle that we put over a double integral like that indicates it's a closed surface. It could be a sphere, it could be an ellipsoid, it could be a cube, okay? It's just got to be closed. And this is a flux integral that we're looking at. And you're computing essentially the fluid flow across the surface, so it's not a curve anymore. Let's change it to a surface, okay, a closed surface, and presumably there's some source of flow inside the closed surface. So you think of it as just some fluid that's kind of passing through the surface that you think of as like a porous membrane, like a filter, and the liquid just pours out of it. And turns out that you can find the flux by just measuring the divergence of this field, which is sort of providing this fluid flow, okay? But because you're in space, it needs to be a triple integral. So you can compute the flux by just noting how much the field diverges. So diverging fields, remember, are ones that push outward from some source. And so there's a source of fluid flow. And if you just sum that up over the region, that's just the total flux across the surface. So we're just sort of adding up how much fluid is flowing outward. And this is a per unit time, okay? And let's say let's call the region inside here Q. Okay, so the surface, it's best to draw a little picture, I guess. And again, the surface is S, but inside we have a solid, which is, or a region inside three-dimensionally, that's Q. Okay, so what we have is this is only possible if vectors are divergent over all in, not R, but Q now. Okay, and just as a reminder, div F is del dot F. So it's very common in physics not to say divergence. We like to say divergence in math. I think we say divergence a lot in physics, but when we write it, we usually say divergence is just del dot F and don't use the div F notation as much. At least I know in Maxwell's equations and other equations in physics that they tend to use the del operator when they write these things out. Okay. So these are all computations that you know how to do here. So there's not, other than understanding that you're able to talk about how flux across a closed surface requires a field that is divergent, or you could say it's convergent. Remember that when the divergence is negative, then you have an inward flow, and we call it to a point that we call a sink, where the fluid sort of drains away, it disappears, but you have fluid coming in to a surface when the divergence is negative. And of course, if the divergence is negative, then the flux has to be negative, which just means that the fluid is coming in rather than going out. Okay, I think I'll add one more reminder, and that is it is customary to have an outward normal for closed surfaces. So here's my ds. And just a reminder, normal is outward for closed surfaces. Okay. And so I would just like to do a few problems. Again, these are all computations that you know. The divergence theorem is sort of beyond, the proof is sort of beyond where we have time or mathematical ability to go, although we did prove it in 2 dimensions. So we're just going to kind of let it be at that point. There is a bit of a proof in the book that works for certain types of surfaces that you can look at. But for now, let's just sort of verify the theorem. Okay, so first example we want to do is a vector field F, and it's going to have components y squared z to the third, comma 2yz, comma 4z squared. Okay. And the surface is going to be basically the boundary z equals x squared plus y squared, so that's a paraboloid. And z equals 9. Okay, so and these are boundaries for the solid Q inside. Okay, so maybe just a quick sketch. You've seen paraboloids many times. I'm going to move my ellipse in place after I draw it because that works much better. Okay, now just keep in mind that is sort of a lid on top, so it's not an open paraboloid. Okay, so this top, I think we'll call S1. Okay, and the bottom is going to be S2. All right, and I think, of course we can put in a z-axis popping out of that thing, so maybe I'll do that real quick. And I'm going to sort of hide my z-axis inside there, but my x-axis and y-axis are here. Like that. Okay, and so I think we'll do the flux, which is going to be the hard part. Okay, so let's get this part of the integral here, or part of the divergence theorem. We'll do the left side. And just paste that in down here. Okay, so we're going to need to break this into two integrals. This closed interval over S, and I guess I could say that S is the union of S1 and S2. So we're combining those. And so this double integral over S is going to have to be broken into two double integrals. One over S1 of f dot ds plus another line or surface integral over S2 of f dot ds. Okay. Okay, so here we go. Let's do the S1. That looks like it'll be easy. So over S1, we can maybe start with ds. And I should say S1, z is a function of x and y. I'll say f1 of xy. Z is just 9. Okay, so that's a function of x and y, sorta. So ds, you may remember, and this has got to have an upward normal on this because the normal has to point outward, and on top, outward is upward. Okay, so ds is, the formula we gave is negative fx, and I guess it'd be f1x. So let me do it this way. Negative f1 sub x, negative f2 sub x, and 1, and that'll have a dA associated with it. So taking partials, oops, and I'm sorry, I screwed up on my, this should be f1 sub y. Okay, and so you're going to get, because f1 is just 9, you're going to get 0, 0, 1. dA, which is just sort of a upward pointing area differential, just points straight up. And it is in fact k, the unit vector k times dA, but we'll leave it like this. Okay, and so now when we do f dot ds here, this is easy, just doing 0, 0, 1. Oops, let me change the order on that. So let me put the field in first. So oops, wrong thing. Try again. Like that. And then let's do this dot product. So easy, right? It's just 4z squared dA. Okay, any questions? No, there's no questions, of course not. So then let's do our double integral of over S1 of f dot ds. Okay, so this will be a double integral. And now we're going to have to think about what we're integrating over. We'll do that in a moment. But this will be 4z squared dA. Don't forget z is 9, so that's just going to be 4 times 9 squared. And we're going to be integrating over a region in the xy plane, and which is just going to be a circle. And so we kind of need to know the radius of the circle. Z is 9 at the top here. Okay. And if we could just copy that circle and paste it down in the xy plane, that's what we're talking about. Integrating over. I'm going to move this because it's not going to look good, but well, I don't know, maybe I could make it look good. I don't know. Oops. So I'm just going to try and erase this out so it's sort of hidden behind the surface. Okay, so that's the projection. This is our region R that we're integrating over here. Okay, so that's your circle. We just need to know sort of the radius of the circle. So that's where x squared plus y squared equals 9. Setting the two equal to each other. I guess up here really is where x squared plus y squared equals 9. So that's a circle of radius 3. Okay. That's beautiful. Okay. So I guess we can take another step. Do a 4 times 9 squared. Let's leave the dA there. We could go into polar coordinates, but I don't know what 4 times 81 is. I guess I could figure it out. Okay, but we just have a double integral over R dA, like that. So that's just, so what's 4 times 80? That would be 324? Okay, and then times the area of R. So this is 324 times pi times, this is a circle of radius 3, right? So it would be pi times 3 squared, right? So what's 324 times 9? So it's 29/16 pi. Okay, so that was over S1. Now we have more. S2 is coming. So here we go. Over S2. Well, ds will be, I guess this bottom curve, I'm going to have z equal to x squared plus y squared. That's fine. That's going to be my f2 of xy. Okay. So my ds, now this has to be a downward normal, so we're going to do f2x, f2y, and again a downward normal has to have a negative 1 there, so I just took the negative of the normal ds. So here, with respect to x, I guess we're going to have a 2x. With respect to y, we're going to have a 2y. And then a negative 1 dA, like that. Okay, so I got my ds worked out. And now we have to do, and that's DSA vector ds. And now for flux, we have to do f dot ds. So let's do that, f dot ds here. Okay, so I'm going to copy and paste that field down. Okay, so this is the dot product we need to do. Okay, so let's see here. We're going to have a 2x y squared z to the third plus, looks like to me, a 4 y squared z and then plus, minus 4z squared. Okay, and that'll be dA. Okay. At some point we're going to have to recognize that z is x squared plus y squared. And it might be good at some point to just start substituting, or to decide what coordinate system we're going to integrate over. This is going to be over that same circle. So unfortunately, I think we're going to have to go to polar. So don't forget that z is x squared plus y squared on this surface. And that's just r squared. So whenever you see z, we're going to put an r square in. Obviously x is going to be r cos theta. Y is going to be r sine theta. Okay. We know what dA is, here goes. Ready? This is not going to be pretty. So you're going to get 2r cos theta times r squared sine squared theta times z to the third. That'll be r to the sixth. Then plus 4y squared. That's going to be r squared sine squared theta times z, which is another r squared. Okay. Now minus 4z squared, that's r squared squared. Like that. And I think we could put a dA outside there. A lot of combinations, I guess. On the first one, you're going to have a 2. I see an r to the 8th plus one more r, so that's 2r to the 9th. Cos theta sine squared theta. Like that. And then plus a 4r to the 4th sine squared theta. And it looks like minus 4r to the 4th, like that, and then dA. Of course, dA is going to get an r d theta. May as well do that now. So, okay. So in the end, we're going to get a, and it looks like we can factor a 2 out, but we'll do that later. So there you got a 2r to the 10th cos, and of course parentheses, cos theta, sine squared theta, plus 4r to the 5th sine squared theta, minus 4r to the 5th, and that'll be dr d theta. I'm just checking my work now. Looks great. Okay, so we're going to do the integral, double integral, over S2 of f dot ds. Well, you know what? We should probably figure out. Yeah, no, we did. So we'll say it's a double integral of this mess that I am not going to write again. I'm just going to copy and paste that. Maybe squeeze it in a little. And put limits on. So r is going from 0, it's a circle of radius 3, so 0 to 3, and then theta from 0 to 2 pi. Like that. I'm going to give you kind of a quick version of this. Okay, so I'm going to factor 2 all the way out. Okay. And the first double integral is going to be a double integral 0 to 2 pi and then 0 to 3. And you're going to have this r to the 10th cos theta sine squared theta. And then I'm going to go ahead and put my dr d theta here. Factoring that 2 out, the next double integral with the same limits would have, well, a 2 out front because I factored the other bit out. Let me just give a little space to myself there. So you're going to have that r to the 5th sine squared theta. And then minus another double integral. Oh, this will have a 2 up front also. So I can catch that. 2 double integral of r to the 5th dr d theta. Looks like I forgot that on the prior, so let me get some of these things straightened out here. I'm just out of space. Okay. Oops. All right, so maybe I'll write one more step before I just start telling you how they come out. So actually, what I did was I broke this up a little bit. So I'm gonna erase something real quick. I forgot my parentheses anyway. So So the first integral is a product of a function of r and functions of theta. So you could break that into two integrals, 0 to 2 pi, just on d theta there. Okay, so that's simple enough. And then the next one is not simple. 0 to... that is a big mistake, sorry. So my mistake. So the theta part has got a cos theta and a sine square theta. Okay, so that gets the d theta, my bad. And then times another integral, this one's the easy one, so from 0 to 3 of r to the 10th dr. Like that. Okay, and then plus, same thing on this next one. You could do plus 2, do an integral from 0 to 2 pi, and just have the sine square theta d theta. And then another integral from 0 to 3 of an r to the 5th sine square theta. Sorry, just an r to the 5th here. dr. And minus 2 more of those. So again, we're going to have minus 2. There's an integral from 0 to 2 pi just with a d theta. And another integral from 0 to 3 of r to the 5th dr. Okay? So that's... And we're getting to the point where this boils down pretty easily. On this one, u would be sine theta, and du is straightforward cos theta, d theta. On this next one, that's a straightforward sine squared theta is 1 minus cos 2 theta over 2, which will cancel that other 2. Okay, so here you'd have the 2. You'll have an integral of just u squared du. And when theta is 0, the sine theta is 0. And when when theta is 0, u is sine 0, so that's 0. And when u is 2 pi, sine of 2 pi is also 0. So this integral ends up going 0 to 0. Okay, so there's nothing to do there, and it doesn't. This next one doesn't matter. So it's 0 to 3. You've got this r to the 10th dr, and of course this whole thing is going to be 0. Okay. The next one, you've got this plus 2. Well, I mean, there's going to be a cancellation, so let's leave the 2 out and just say we've got an integral from 0 to 2 pi. And inside you're just going to have that 1 minus cos 2 theta there. And we'll think about that. The r to the 5th, can we just say that's going to be 1/6 r to the 6th from 0 to 3 for that. And then you're going to have it again, minus 2. Integral from 0 to 2 pi d theta will just be 2 pi. And then that r to the 5th, so you're going to get a 1/6. Yeah, it'll be r to the 6th. Why don't we just say times 3 to the 6th there? And then I could have done the same thing on that last one, so I think I'll clean that up. That's just going to be a 3 to the 6th. Here. Okay, so this is actually really tidy. Okay, so the first one, don't even have to think about it anymore. So we got this first integral, so I guess we're going to need parentheses. Okay, so we still have that 2 out front, so let's keep the 2. And then the integral of 1 minus cos 2 theta, so that'll be theta. Antiderivative of cosine is just sine, so it's going to be minus 1/2 sine 2 theta and that'll go 0 to 2 pi. So of course this part's just going to be 0. Okay, the theta also goes from 0 to 2 pi, so that's going to be 2 pi. Okay. And then 3 to the 6th over 6, couldn't we say that's 3 to the 5th over 2? So it'll be times 3 to the 5th over 2. And then minus, I think, a 4 pi. Times 3 to the 6 over 6, which we again could call 3 to the 5th over 2. And that I know there's more simplifications in there. Okay, let me close off the parentheses here. Okay, I'm just sort of trying to catch any mistakes. I think, so remember there's a 2 times everything here, so the first part of this just has 2 times 2 pi, so that's 4 pi times the 3 to the 5th over 2. So I think that ends up just being 2 pi times 3 to the 5th over 2, and then minus 4 pi times 3 to the 5th over 2. Like that. Oh, but the over 2, I'm multiplying a 2 through this. So why would I have an over 2 there? And I think on the first one I failed to multiply the 2 through. So that would also have no 2 there. Now I'm going to double check this. I'm not convinced. So 2 pi minus 4 pi. I think we're good here. So I think I'm getting negative 2 pi times 3 to the 5th. Okay, so in the end, that's negative 486 pi. Okay, isn't that lovely? Gorgeous. Okay, so and then of course that was just half of the integral, so we broke this down into 2 integrals, so let's put them back together again. Okay, so this is what we're doing. Okay, so the first one was somewhere up here, 2916 pi. And then the second one was minus 486 pi. Okay, so looks like 2,430 pi. Isn't that beautiful? Okay, so that's done. Now this is supposed to be equal to the divergence, right? So let's get back to the divergence theorem. Way up at the top here. And see how it comes out if we do it the opposite way. So we're going to need to do the divergence of our field real quick. So div f is defined to be del dot f. Okay. And just as a reminder, del is just a partial derivative operator vector. That's a y. I don't like it. Okay. And then let's just copy and paste our field down wherever it is. They're way up there. Maybe a little smaller. Okay. Right. So, so the derivative, the partial of the first component with respect to x. I guess I could write this out. So you get partial with respect to x of y squared z to the third plus partial with respect to y of 2yz plus the partial with respect to z of 4z squared. Okay, so that's the divergence. Do the derivatives, so you get 0 plus 2z plus 8z. So I sort of love that. So it's 10z squared. Okay, that's great. Did I say 10z squared? Let's go with 10z. Okay, so now we're ready to integrate this. We'll see what coordinate system we end up with. So, so this is equal to triple integral over our solid of div f, which was 10z, dv. And maybe let's paste our surface back down here. There it is. I think it might be a good idea to put this into cylindrical coordinates. So for the top, remember z is x squared plus y squared, and we should just say that that's r squared. No, that's the bottom. Forgive me, that's the bottom. Okay, so z is just r squared on the bottom. And of course z is 9 on the top. Okay, so z is a nice function of r on bottom and top. So why don't we just do this in cylindrical coordinates, because z gets to be one of the coordinates in cylindrical. So you would do it this way. Triple integral of 10z dv would be r dz dr d theta. Okay. Z has to go from r squared to 9. Okay. R from, I believe, 0 to 3. And theta from 0 to 2 pi. Like that. Okay, so here we go. Okay, so we're integrating with respect to z first, so why don't we do a 5z squared, where z goes from r squared to 9, and then we'll put our r d theta in. So that's a little ugly. I guess we could put that 5 out, right? What's it doing there? Okay, so we're gonna have like a 9 minus 9 squared minus r to the 4th. Don't like it. Don't forget there's another r and a dr d theta. Okay, let's multiply that out. So you get the 5 integral 0 to 2 pi. I think that theta is just not even caring about r, so let's just do a d theta there. And then the next integral from 0 to 3. And so we're going to have an 81r minus r to the 5th. Like that. And there's a dr d theta. Oops, I already got my d theta in there. Okay, so 5 times 2 pi. So that would be 5 times 2 pi times, in parentheses, we're going to have 81 over 2. That'll be r squared from 0 to 3 minus 1/6. This will be an r to the 6th from 0 to 3. Like that. I think I'm going to run this 2 here into it to cancel the 2 and make that a 1/3 inside. So if you look at it this way, we're going to have a 5 pi out front. And inside, you're going to have the 81. There's just going to be 3 squared. So this will be 3 squared. I'm not going to multiply that out. I want to remind you 81 is 3 to the 4th. Okay. Now I've run the 2 in. So here I'm going to be subtracting 1/3. And then there will be a 3 to the 6th. Like that. So I think if you look at this a little longer, you see this is 5 pi, and I think it's just a 3 to the 6th minus 3 to the 5th. There. And maybe factor out 3 to the 5th. So it's 5 pi times 3 to the 5th times 3 minus 1. So that's 2. 10 pi times 3 to the 5th. Do the math. It's 2,430 pi, which is exactly what we got up here when we did the flux through the surface. And so all we're saying is you can't have flux unless you have divergence. A field must diverge. And it turns out if you sum up the divergence of a field inside a surface, that's exactly the fluid flow across the surface. Okay? So the fluid has to diverge from inside. It has to push outward. Okay? And the total divergence is the flux. It's the total amount of fluid crossing through this surface, this filter or membrane per unit time. Okay, so again, I'll just go ahead and say I'd like to kind of reemphasize what we've just shown. This is true. Just for one case. All right? Also, we want to let the magnitude be, let's say, V, and I'll do a script V, and these will be meters per second. Okay. For the surface, first of all, we should construct this. So my field is going to have magnitude V times some unit vector that points away from the origin. So how about if we do V and just make the position vector R into a unit vector like that, and that'll work. Just remembering that R would just, again, being a position vector, would just be X, Y, Z, and then the magnitude of that is standard. Okay, like that. Now, I guess we got to put this all together. So I think we could probably leave the V out and write it like this. So I'm going to cheat a little as I do. Maybe make it a little smaller. If I can pull it off with one hand. Still have a broken arm. So this is not working the way it's supposed to. There we go. Okay, so I don't know if I can squeeze in a Y and a Z like that. So let's see what happens. Here's my Y, and then can I put a Z in? I don't know. Yeah, not quite. So I'm going to make some space here. I think that'll work. Okay, and of course we got the x, the y, and the z on top of those guys, separated by commas. Okay. Okay, so we'll need to know the divergence of this field if we're to do the flux across the surface. So, so the divergence of F is, as you know, del operator dotted with F. Okay, so I think we can put the let's go ahead and put the del in. So we'll have this partial with respect to x, with respect to y and z. Okay, and dot that with this thing. And I think I've decided I'm going to put the v inside. So, oops. And maybe I can shrink it down a little too. There we go. Oops. Now, these derivatives are all going to be really similar, so I'm just going to do the first one. So maybe off to the side, let's do this first partial derivative. Maybe I'll just do it down here. And again, we're doing sort of a dot product, so the partial with respect to x goes to the first component here. And this can be a little messy, I think, so we'll see how it goes here. So the derivative of the top is just going to be v times the bottom, which is the square root of x squared plus y squared plus z squared, minus the derivative of the bottom. So here you're going to get a 2x. Well, I'm taking the all right. The derivative of the bottom is going to have a 1 over 2 square root of x squared plus y squared plus z squared. Okay. And then you have to multiply by the derivative of what's inside, which is going to be a 2x, like that. So that's the derivative of the bottom, and then you multiply that by the top, which is vx. Of course, it'll all be over the bottom squared. So we'll just have an x squared plus y squared plus z squared down there. Okay. And with this one, the best way of managing that is to multiply the top and the bottom by the square root. So if we put in the square root of x squared plus y squared plus z squared, I think it becomes manageable. Okay, and so in the end, it looks like you end up with that v there. Oops, let me go back to red. Okay, so it looks like you'll have that v, and you have the square root of x squared plus y squared plus z squared times another one, so you end up with just an x squared plus y squared plus z squared. here. And it looks like you just subtract out, the 2's cancel, you just subtract out a Vx squared. Like that. And then the denominator simply is going to be x squared plus y squared plus z squared. I think that's going to be the 3/2 power. There. And of course there's one more step. We could just call this v times x, y squared plus z squared. Over that denominator. Oops. Okay. So that's the partial with respect to x. And then the partials with respect to y and z, I think, would kind of come out symmetrically to this. So I'm going to assume that, and maybe we can box this one up. And figure out what the rest of this will look like. So, so the way the divergence comes out is the partial of the first component with respect to x gets that v. Oops. The v, and it gets the y squared plus z squared. And that denominator here, I'm going to just copy underneath it. And so that's with respect to x. And then when we do the derivative with respect to y, we're going to have a v, and then I assume there will be an x squared plus z squared here. It leaves the variable out that you're taking a derivative with respect to, like that. Same denominator. Okay. Okay, let's just make a little space here. I think that other thing's getting in the way. So finally, the last term would have the v, and this is with respect to z, so you get the x squared plus y squared in here, like that, and same denominator. Okay, so that's what this is going to end up being. Again, that's the divergence, and I'm trying to make room for everything. Alright, so this is all going to come together. I think you can leave that v factored out, but in the end, you're going to have, if you look at it, there's 2x squares, there's 2y squares, and there's 2z squares. So if you put a 2v out front, there will be the x squared plus y squared plus z squared, and that's to the just to the first, and then it's over the same thing to the 3/2 power. Which I think is just 2 times the speed of the fluid flow over the square root of x squared plus y squared plus z squared. So that's the divergence of this field. Okay? And then let me box this in over here. Or circle it. I don't know what, that's not a box for sure. Okay, so we've got that, and then what I want to do again is to compute this curl. So let's this flux. So the flux of this field F, we're going to do through S, which is going to be a sphere of radius A. Okay, so flux through a closed surface. You take the field and you dot it with ds, which is that outward normal. Because it's a closed surface, we always use an outward normal. But you can also evaluate this with a triple integral over the divergence. So Q is the solid inside the sphere, or the shell of the sphere, and then we can do the divergence of the field dV. So that again is the divergence theorem. Okay. Okay, so let's keep going. So we have the triple integral. The divergence of the field is just twice the velocity of these, I should say twice the speed of these velocity vectors over the square root of x squared plus y squared plus z squared. Like that. And dv, I think at this point we want to put this into spherical coordinates. So let's do that real quick. Okay, so 2v, but in spherical coordinates the denominator is just rho. And dv should be rho squared sine phi. And then d rho d phi d theta. Okay, rho goes from 0 to the radius of the sphere, which is a. Okay, phi always 0 to 2 pi on a sphere. Sorry, 0 to pi. From North Pole to South Pole is pi radians. And theta all the way around 0 to 2 pi. Okay. Notice there's just a row to the first in all of this, and we can kind of break this up into 3 integrals. So you could do an integral of 0 to 2 pi just on theta. There's no function of theta here, so we'll just put the d theta there. Okay, and then maybe we could do phi next. So you'd have an integral from 0 to pi, and here you'd have the sine phi d phi. Like that. And then an integral from 0 to a. And here you would just have rho. D rho. Okay. And maybe out in front of all of this, we could put the constants, which are 2v, I believe. 2 times the speed of our velocity field. Okay. Well, let's see. We've got 2v. Oops. Times the next integral will be just 2 pi. The next integral we can call negative cos phi, and we'll have that go from 0 to pi, and we'll figure out what that is in a second. Here you're going to have 1/2 rho square from 0 to a, so that'll be 1/2 a squared. Like that. Okay, so let's see here. I think we can cancel one of the two, so I think I'm going to just get rid of one of these guys. And the cosine, you get the negative cosine, well, let me put this down. So you've got a 2 pi, 2v pi, I guess. And then the negative of cosine pi will be positive 1, cos pi is negative 1, and then it'll be minus the negative of cosine 0, so that'll be minus negative 1. Okay, lots of double negatives there. And then over here you'll just have an a square. And so I want to go ahead and point out that this is 4 pi a squared times v. Okay, and this is the area of the sphere. Okay, and an area that would be in meters squared. Okay, and then of course v is the speed, and that'll be meters per second. Okay, so if you do the units for this, what you get is the area of the sphere times v, and then the units would be meters cubed per second. So meters cubed of what? That's a volume. Okay, so what you're looking at is a volume of fluid that's flowing across the sphere per second. Okay, so let's just wrap this up and say this is equal to the volume flowing across the sphere per second. Okay, so that's why we say that flux is just the flux of a field across some surface. If you think of the field as a fluid flow, then the flux is just the total fluid, the volume of fluid that flows across or through, if you like, this filter. If you think of the surface as a filter, per the volume of fluid through the filter per unit time. And so you're just kind of totaling up how much that surface or that filter can absorb of this fluid that's flowing into it. So in a sense, flux is a sort of a measure of absorption. Okay. All right, so I think that wraps this one up. So good luck with 16.9.